So today we will have 5 talks, including myself. The next presentation, which will be given by myself.
Good morning and good evening, everyone. I'm Shu-Chih from National Central University in Taiwan, and today I'm going to talk about the application of GNSS-R wind to weather prediction, and my topic is the impact of assimilating the GNSS-R wind data on severe weather prediction, and this work is mainly done by our research team, including Chen Jiegao, Guanren Lin, Guanghui Lu, and Yiping Zhang. So we know that the low-level atmospheric condition has the key information for the development of the severe weather system. For example, the low-level convergence and the low-level moisture transport can be very crucial for the tropical cyclone intensification. And for weather prediction, over ocean particularly, we rely heavily on satellite data. And currently, we do have different types of satellite wind products, such as the air motion vector and the accelerometer winds. However, they are less satisfactory in terms of the spatial and the temporal resolution. So the fact is that we still need near-surface observation over ocean and for the severe weather system prediction. And GNSS-R wind provide a great possibility for a broader range of wind speed measurement under all weather conditions. So the goals of this study is to explore the impact of GNSS-R wind data on regional severe weather prediction, and we would like to understand the potential and limitation of the R-wind data assimilation. And we would like to incorporate R-wind with other types of observation, and we would like to note whether we can have more applications. So the outline of today's talk is I will talk about the impact and the challenge of assimilating the ocean surface wind speed data on heavy rainfall prediction. And we will present results from OC experiment and also real case. And we incorporate the GNSS-R wind in the high resolution data assimilation framework and to assimilate both the radar and R wind together. And the last, I would like to briefly talk about how we can use the R wind data for our TC parametric wind assimilation, and particularly for the intensity prediction. So before I start, I would like to use this slide to briefly illustrate the concept of data assimilation. So data assimilation is a state estimate methodology to combine information from different sources. And with the purpose of improving numerical model prediction, data assimilation combined observation and also model states. So observation, which are usually regarded as a noisy truth and usually have inhomogeneous distribution. And in contrast, model forecast, which has information everywhere over the model domain due to the use of model governed by dynamic equation. So data assimilation try to best combine observation and the model and bring synergy. So in our application, we have GNSS-R wind and also we regional the weather model. For the first topic, we would like to explore whether assimilating ocean surface wind data can improve the wind analysis and later the precipitation prediction for the heavy rainfall event on June 2nd, 2017. And this event is governed by synoptic scaled front and warm and moisture air by southwesterly that bring a lot of moisture in, and local barrier jet, that's the interaction with the topography. And within one date, we have total precipitation amount more than 300 millimeters. But before I get into our investigation of the real case, I would like to discuss the impact and challenges of assimilating the ocean surface wind speed using the observation simulation system experiment. And for the OC, we generate the 1 kilometer nature run And as you can see that the right-hand side is the total accumulated rainfall from the nature run. With the nature run, we can well reproduce the features of this heavy rainfall event. And for the data assimilation experiment, the model is initialized with inaccurate condition. So we are trying to recover the accuracy of the near-surface wind by assimilating the ocean wind speed data. And we are using the regional data assimilation system, the WRF, the local ensemble transform common filter. And we have the 27-kilometer analysis, and the assimilation is done every 3 hours, and we are using the 42 members. And we have the mainly two experiments. The first one is the control run, which assimilate the conventional weather data and other satellite wind. And for OWS, that's the one that additionally assimilate ocean surface wind speed data and is available everywhere over the ocean grid. And the observation arrow setup follows thickness. Here, although the ocean surface wind observation is available at all ocean degree points, this is to highlight the impact of assimilating ocean surface wind, and temporarily we would like to ignore the issue of data density. We have to emphasize that even we have data everywhere over the ocean, that doesn't mean we can improve the wind accuracy everywhere. So here are the arrows for the wind speed and wind direction at the surface. So first, you can see that indeed assimilating the ocean surface wind, we are able to reduce the wind speed arrow. Okay, so that means the assimilation is effective. However, if we look at the wind direction arrow, we can also see that there's degradation in the area where the front locate. If we group the wind speed data according to the wind direction arrow, we can see that the wind speed improvement decreases with the increase of the wind direction arrows. And even we assimilate the perfect wind speed, you can see that there's not much improved with the perfect wind speed. So the degradation in the front area is a serious concern, since it can affect the intensity and the location of the heavy rainfall. To investigate the sensitivity of wind speed arrow to the wind direction arrow, we conduct a series of assimilation experiments by assimilating perfect wind speed, but incrementally increase the arrow in the wind direction. So we increase the wind direction arrow every 15 degrees for each experiment. So totally we have 13 experiments. And from this figure, we can see that it seems that there's a turning point that the wind speed arrow become larger than the background arrow. That means the assimilation degrade the wind accuracy or degrade the wind speed. On the other hand, this also shows that as long as the wind direction arrow is smaller than 60 degrees, the assimilation is still effective. So this result suggests that the accuracy of the wind direction is a key for using the wind data effectively. So based on this, we would like to investigate two strategies. First is a two-stage update. So we first assimilate all other observation first, and then use the analysis as the new background and to assimilate the ocean surface wind, so that it assumed that at the second stage we will have the better wind direction. And the second strategy is that with the wind speed data but then we generate synthetic the wind vector, choosing a representative the wind direction. And the representative the wind direction is based on the ensemble mean. So, which is about, has a wind direction error of 32 degrees for this example. Here I'm showing you the horizontal map of the wind speed and the wind direction arrow using the two strategy. So first you can see that if we prescribe the wind direction, even though it is using the mean state of the ensemble, the background ensemble, you can see that there's large reduction in the wind speed, and also the degradation in the wind direction now disappeared. And for the second strategy is the two-stage assimilation. Unfortunately, for this one, we still have the wind direction degradation here, but you can still see that with this strategy, it can still reduce the wind speed error compared to the original one. Now let's look at the mean square error of wind speed and the wind direction grouped by wind direction error. And the red line here are the background error. And the blue line are the analysis of error from the original experiment of OWS, which assimilate ocean surface wind speed. So first, let's focus on the green line here, which use the prescribed wind direction. So you can see that with the prescribed wind direction, the wind speed error can be reduced effectively, and for the is less sensitive to the wind direction, the amplitude of the wind direction error. And for the wind direction, you can see that because we are using the prescribed wind direction, and the prescribed direction is taken from the background mean, so that there's no degradation on the wind direction, but there's also no improvement neither. And then if we look at the two-step assimilation, which is the light blue line here, you can see that the improvement is relatively small compared to the other strategy. But we think that this relative small improvement is because that at the first stage, the assimilation, we have relatively less observation over the ocean. So that's why that we don't have much information to correct the wind direction. And this maybe could be improved if we have more other data. So then based on the experience from the OC, and then we go ahead and conduct the real case experiment. And basically it's the same setup with the OC, except that we assimilate thickness data at 15Z. And in the following, we will be looking at the control experiment, RWS, which assimilate wind speed, and RUV, which assimilate R-wind as the UV, the wind component, with the wind direction prescribed. So for this period, we actually have limited thickness data. Nevertheless, the observation locations are not bad and largely cover the front system at this location. And the figure at the right shows the ECMWF wind speed and thickness wind speed. As you can see that near the front, there is stronger wind speed, and this is related to the low-level jet, and the relatively low wind speed northeast of Taiwan. And you can see that the thickness wind speed generally agreed with the ECMWF wind speed pattern. So here I'm showing you the first level, the wind correction. So you can see that with the R-wing data assimilated, it's clear that we can have significant and front-scaled wind correction. For example, the correction on the zonal wind component shows convergence north of Taiwan, and while the correction on the meridian wind shows modification on the for the wind the front orientation. Now we compare the wind speed analysis. So first, you can see that with the assimilation of Cygnus wind speed data compared to the control run, over this box region, you can see the wind speed is increased. And with the RUV, which means the wind direction is prescribed, you can see actually the wind speed analysis is quite different from the other two experiments. For the high wind speed area, now the wind speed is further increased, and also for the wind speed northeast of Taiwan. And this pattern seems to agree even better with ECMWF. So by looking at the zonal cross-section over the northern tip of Taiwan, we can see that first, with the simulation of wind speed data, indeed, we are able to increase the wind speed over low-level atmosphere. And with RUV, the wind speed is not only increased significantly, and also the moisture, which is indicated by the color shading here, is also increased significantly. That means that with the increase of the wind speed and also the moisture amount, we are able to enhance the moisture transport. And with this slide, we can see that now with the simulation of the wind speed data, we can better represent the characteristic of low-level jet, and also the impact can be identified in the moisture field. So finally is the impact on the precipitation. Here, this slide shows the one-day rainfall accumulation. So first, you can see that the control run already did a nice job in rainfall prediction. However, you can see that the rainfall over Taoyuan, this area where NCU locates, is over-predicted. So you can see a positive rainfall arrow here. And this is because in the control run, the front system moves southward too fast. And with RWS, it's clear that the over-prediction over the Taoyuan city is now alleviated, but there is still large negative rainfall arrow at the northern tip of Taiwan. This is because now the front does not push that southward like the control. And with RUV, the reduction in this heavy rainfall area is significant, and especially for the north of Taiwan. And we also observe that in the RWS run, there is unrealistic rainfall, and it does not appear in the control run. And so this is the example that assimilating the wind speed data can introduce error in the wind direction and lead to the rainfall error here. But with RUV, you can see now such unrealistic rainfall is reduced. So so our conclusion is that with the simulation of the wind speed data, now we can provide effective correction for heavy rainfall prediction. Even for this example, we only have limited amount of Cygnus data. So for the next topic, we would like to investigate the potential impact of combining the R-wind with the coastal ground-based radar. So like this example show, this is the Typhoon Hato 2017. So you can see that for this typhoon, it passes through the Bashi Channel without affected by terrain. And the typhoon gets intensified continuously and can cause a great damage later. So for this kind of typhoon, it can be observed by our Canadian radar, which locates at the southern tip of Taiwan, and assimilating radar data may provide a great chance for improving TC intensity prediction. However, there's one serious drawback of radar measurement, which is it cannot observe the near surface wind conditions. Therefore, we investigate whether the R-wind data could compensate such limitation and further improve the TC prediction. For this study, we use the WRF LVGKF radar data assimilation system to assimilate radar radial velocity and reflectivity and R-wind. And the different from the previous experiment and other experiment using the R-wind data, the assimilation is performed with rapid update. But that means we did the assimilation every 15 minutes and at a high resolution analysis grid, which is 3 kilometers. Here I have to emphasize that we are doing the rapid update every 15 minutes and the assimilation period is only 3 hours. So at each analysis cycle, we have the very small amount of data compared to the radar observation, but as we will see in the next slide, we can still have large impact with this amount of data. This slide shows the TC structure in terms of the azimuthal average, tangential, and the radial wind component. On the left, the second row here are the experiment using the default assimilation setup, which adopts a short localization that we commonly use for convective scale data assimilation. The third row is the experiment using the multi-scale correction for radar data. Here, we use the successive correction localization method for multi-scale correction and in order to consider the horizontal scale of the TC. So we can see that first, if we only consider assimilating radar data only, we can see that with the multi-scale correction, the TC circulation is much stronger than the one that using the default assimilation setup. To illustrate the impact of R-wind, we show the improvement relative to their counterpart that assimilate the radar data only. So first, you can see that with the assimilation of wind speed data, the wind speed, the improvement is significant in the control experiment and mainly locates below the 2 kilometer and for the tangential wind. And with this improvement, the TC circulation is enhanced greatly. And you can also see that with the multi-scale correction, the impact of the R-wind can propagate to upper level. This should be related to a stronger and more organized TC structure. So also, there's clear improvement with the radial wind component. Although we are not really expecting that assimilating this amount of ocean surface wind speed data can improve the track prediction, but we do see that assimilating those data can remove the northward tracked arrow shown in the experiment with the radar data only. And in terms of the intensity prediction, which here I show the minimum sea level pressure and the maximum wind speed, we can see that for the control run, assimilating R-wind data has a clear impact on intensity prediction. And with the multi-scaled correction framework, the intensity performance are comparable between experiments. The one with surface wind speed assimilated seems to have stronger intensity, closer to the nature run. But this should be due to the slower TC movement, and the TC made its landfall later than the other round. For the last topic, I want to briefly present that we plan to include R-wind data in our TC-centered assimilation framework. The TCC-LTK framework is developed to better represent uncertainty of vortex structure and using the inner core observation more effectively. The main idea is to relocate the TC in each member of the ensemble to the observed location so that the large uncertainty due to the displacement of the TC location can be avoided. Since over northwestern Pacific region, we usually don't have the inner core data unless there's special observation experiment. So we assimilate synthetic observation of surfaced acid symmetric wind profile. And this is defined as the mean tangential wind, and following Willoughby 2006, which used a set of formula to characterize vortex wind structure. So on the right-hand side, it is the example of Typhoon Maggie 2010. So you can see the tangential wind profile change in time with different intensity. Following the work by Morris and Ruft, we can use the R-wind data to estimate the TC size, which is defined with the radius of 34 knots. And here is an example of Typhoon Kurosa 2019. So you can see that at this time, Cygnus actually has a very good coverage of this typhoon, and the size is well estimated by the Cygnus data. And compared to JTWC and JMA, the estimation is reasonable. And we can also use this to construct the TC parametric wind. If we look at the size estimation, also with the Typhoon Kurosa, at different times and for different quadrant, you can see that Cygnus estimate size generally capture the development of the TC size and is able to show the differences in different quadrant. For example, the southern part of the TC has larger size. So by combining the size estimation from the R-wind and our own profile estimation, we plan to adjust our original mean tangential wind profile with the Cygnus estimate and investigate the impact on intensity prediction. Finally is the conclusion of today's talk. First, we saw that assimilating the GNSS-R wind data can have good impact on regional wind analysis and heavy rainfall prediction. However, we should be careful about the degradation on wind direction. The impact can be further optimized by adopting strategy that assimilating the synthetic wind vector or the two-stage assimilation. R-wing can complement the radar data, which is not available near surface. With the rapid update high-resolution the DA framework, R-wing can be used to improve the TC analysis. We suggest that the R-wing data should be assimilated under a multi-scaled correction framework, which optimizes the use of radar data. At last, Cygnus R-wing data can provide robust estimate of TC size, which can be further used for TC parametric wind assimilation and for the intensity prediction. Thank you very much.
Okay, thank you all. Anyone have questions?
Hello.
Yes, Shia.
Hi. Thanks for the great presentation. So actually, I have one question for both Professor Pu and Professor Yang. So from Professor Pu's study, she showed that data signaling is very important for the R data assimilation. However, in Professor Yang's study, I think you don't use the data signaling, right?
No, we didn't use data signaling.
So I know different data simulation may have a different simulation strategy. But I'm thinking, do you have any recommendation for people who want to use GNSS-R data for the data assimilation? Should they using data signaling or not?
Professor Pu.
Let me comment on this. So I think if you only assimilate the one data type and not assimilate any conventional data, you can use whatever strategy you use. And so in that way, so when you assimilate data, as long as your data assimilation system works, you can get positive impact. But so for my study, I actually assimilate all the conventional data available with the Cygnus data order for the integrated data assimilation efforts, because you already have a lot of information already there. So if you do not do data signaling and do not work on these Shu-Chih and this, so perhaps you are not seeing the data impact. So that's it's usually different when you only assimilate the single type of the data, or you assimilate the many data together. Because why we need to do the signaling is because, as I said, in the data assimilation system, you assume this information are uncorrelated. But because you have the many data source and the information redundancy, and also during this retrieval process, so you retrieve the product, the data may correlate. So this prevent you get some positive impact. That's why the data signaling is needed. So I think that my answer to you is really up to you. If you if you work on a single data set and you get a good impact and you feel satisfied, it's completely fine. But if you want to get the best, you can try the different methodology. And in the meantime, for the integrated data assimilation environment with many types of the data available, you got to work hard and on this strategy in order to best utilize the information.
Okay, I just briefly respond this question. Actually, we assimilate including all the data we have, including conventional data and also the satellite, the AMV data, and the Cygnus data. But so far, what the difficulty we have actually is that for the coverage, in terms of the coverage, it's not enough. So, and also, as you see that in my presentation, that even though we generate ocean surface wind data independently, we still see and we have a lot of data over ocean, but we see this degradation on the wind direction. So we would like to first solve this kind of difficulty first, and then and later, after all the components are set, and then we will try to see if we should optimize the use of the wind speed data. For example, whether we should do thinning or whether we should consider including the observation error correlations in our framework, which has been actually included in our radar data assimilation framework. So for that, I will also suggest that maybe we should also take a look whether and how, and for this data set, the sickness data, whether there's really the error correlation, observation error correlation existed in this data set. Yeah, so that's my answer, I guess. Yeah.
Okay, so I think the Shu-Chih make a good comment here. So then there are two things we need to consider. The first thing is, so there's in the sickness science team, there already have some of the study from the Chris Ruff's group, and they investigate this correlation between these data, and so they have some results, and we haven't really looked detail for the data assimilation. So that's the first thing. Another thing is also the data assimilation system is a complicated system. So it's really what I present mostly based on the mature system, which is already operational system. And with the operational system, there are first thing is many of the other data of the assimilation, we will not touch them. They're already there. And so then we work on what we add on. But for your case, since you work on the research model and you have different type of the data, so you have more button to tuning. So you can choose whatever the strategy you want. But my suggestion really is over the years we work on the data assimilation. For the integrate the data assimilation efforts, really, you need to consider many of these factors. So, I mean, how do you think in the data? Shu-Chih's data, it's also rely on your model resolution and also the localization you use for your ensemble system if you use localization for the ensemble. And also what is the length scale you choose for your variational data assimilation. So I mean, there are many of these buttons to tuning, and so then I think it's data sending is important. Given for my results is given the fact that I use the operational system, and there are many other things I should not touch. But for your case, if you work on the research model, you have more button to tune, and you can find the best solution. But I mean, usually, so check with this data impact from this analysis increment is always a good idea to look how things change with you assimilation results, and then you can justify from there and to see why you get positive or negative results. And also, I think this is also the way help us to understand the science question from besides of data assimilation. So for instance, from the data assimilation, in the radar data assimilation, when we conduct for the hurricane Genesis case, what we found is after we assimilate radar data, up-level warming is quite notable. And then we search the nitrate ratio, but the Professor Darling Zhang just finished a work, and they find out this upper level warming associated with surface temperature, surface sea level pressure drop. So then this actually gives idea why the data assimilation get the better results, which also not only helps get the better analysis, but also helps understand how the things process helps the process study. So I mean, it's really data assimilation is a science, not only just use the data, how you best utilize the data, but also from your results, you get better or worse results. You can try to understand the processes.
Okay, thank you very much for Professor Pu's comment. Today, we are very thankful for all speakers and for the great presentation. And we just started our satellite mission for the Triton, the GNSS-R. And we are hoping that there will be more for this satellite in the future. So we are hoping we can keep learning from you guys and wish to catch up and with the progress like all you have. Thank you very much. So I would like to close today's session. Thank you.